Hey guys, Long here, back with another math video. Sorry for the lack of videos recently. Daniel's at Awesome Math, and I've been out too, so yeah. Today we're going to be doing a problem I saw while watching anime. This is from the anime Assassination Classroom. Season 2, Episode 12. I recommend you go watch it. It's a pretty cool anime. And these two characters are on the last question of a math test. And of course, because it's anime, they over dramatize it, so they're actually battling the math question in an arena. So this guy is named Asano and this guy is named Karma. And I thought this question was really good because one guy solves it in an easier way than another guy, and I think the question is good as well. So the essential question, which I'm going to explain now, is that given a cube with side length A, and given that each of the vertices on the corners is a single point, and that there's a point in the center which I will denote as arbitrarily x, given the domain of points inside the cube that is closer to x than the outside points, which are on the vertices, are closer to x on the outside points, what is the volume of this domain? So again, the domain of points in which the point is closer to x than any of the outside vertices, what is the volume of this domain of points that meet these requirements? And that's the question. So pause the video if you need to, try to solve it on your own. And without further ado, I'll introduce both solutions that the two characters came up with, one being much easier than the other one. Okay, so if you were to actually draw out the actual domain of points that are closer to x than any other corner, you get something really annoying. So for instance, you'd actually, let me just copy paste it in. You get something that's like this. I'll resize it so it's smaller. You get something like that. And that shape is really annoying because even though you have like these 8 neat sectors that you can, so the middle shape is obviously like, I don't want to find the volume of the middle shape. It looks like it's made of hexagons and squares and it looks absolutely horrible. I might be able to find the volume of these 8 outside corner shapes, like these things, which is what Asano-kun does. He spends his time trying to calculate the volume of those, subtracting 8 of those from the volume of the cube to get the volume of the inside domain. And that's what the domain looks like, and it looks really annoying, and we don't really want to do that considering that looks really hard. So what does Karma-kun do? Well, Karma basically says, well, this is interesting, but what happens if we actually tile the outside with more cubes? And of course, he thinks of this as like the crystalline structure of salt because of each of these is like an atom or something. Anyway, that's irrelevant. So we each tile these with more cubes, he says, and that will help us. But how exactly does that help us? Well, if you tile the shape with more cubes, you'll see that if we keep tiling, then what happens is something very interesting happens. We see that these center points form a cube of their own. These center points also form a cube that are equivalent to the outside cubes. And after you realize that, you begin to realize that if we tile the entire space with a crap ton of these cubes, including the point in the center of each cube, then the points in the center form their own cubes, and then these corners actually become the center. Like for instance, this corner is the center of the cube made of the centers of the other cubes, which is sort of weird, but just hang in there for a second. So if we connect all the centers of all these 8 cubes, the center of that cube created from the centers of the other cubes will be the center, will be this point, which is actually a corner. So in this essence, the corners become centers of other cubes that are made from the centers of the other cubes. And what I'm trying to say is, just because a point is in the center of a cube, this point is also a corner of another cube. And because of that, all the points are essentially the same. They're all in this lattice. They're on this lattice, and they're actually all equivalent because they can all be the center of a cube depending on how you connect the points, or they can all be part of a corner of a cube. Like this middle point. This middle point is both the center of this cube and the corners of these 8 cubes. So all the points are sort of latticed equivalently in this space, and they're all latticed relatively, equidistant from each other, and they're all equivalent in position, and it's completely symmetrical throughout space. So because of that, let's call the area of the domain A, because A for area and area of the domain, right? So A is the area of this weird hexagon square shape, right? Well, let's just let's say X is the center point, right? Let's say X is the point we want to consider. So for instance, let's have this point be X. Let's have another arbitrary point be Y, and this Y point doesn't have to lie on any of these points, but can be any arbitrary point anywhere. Given Y's position, if you were to randomly drop Y in this space, Y would always be closer to one point than it is to any other point. And yes, you can say that, yes, there is a tiny, infinitesimally small domain of points which are equidistant from like 2 points or 3 points. But the actual domain in here, for instance, consists of points which do not lie on that boundary, and that boundary is negligent in area, so we can ignore those. So basically, the majority of the entirety of the space is consisted of points, arbitrary points Y, which are closer to one point than they are any other point. They will always be negligibly closer to one point than any other point, right? So ignoring the cases where Y is equidistant from 2 points, which is just like a boundary case, like these are just boundaries, and those points are relatively negligible because they don't take up any area. Let's say Y is closest to 1 point. Let's also say that because this space is filled up with an infinite number of Y's, that if every single one of these points is closer to 1 point than any other point. Because of that, we have this conjecture. We say that the entire area of, let's say, since all these points are equivalent, they all have area of A around them. They all have A. And because they all have this area A, this like weird hexagon square shape around them, we have to make sure there are no gaps in between. Now, because we've proven that given any point, they have to be closer to 1 point than they are the others, that means we just proven that the entirety of the space is basically this entirety of the space has no gaps, because there can be no point in the space that's not closer to 1 point than that's not like closest to any point. It has to be closest to some point, right? Except for the boundaries, which take up no area. So every single space in this area per se is taken up by this weird A shape, the weird shape of the domain. So because every point has this weird domain around it, that in which the points near it are closer to it than any other point, that means that this point here also has it, right? It has an A surrounding it. This point here has an area surrounding it. This point here has one. 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 And every corner of the cube inside this area has one. And notice that because this point right here is connected to 8 other cubes, right? This point has 8 other cubes, as shown by this point right here. Since this point has 8 other cubes attached to it, that means its weird hexagon square area A, domain of points which are closer to it than any other point, is 1/8 inside this cube. The other 7/8 are distributed around the other 7 cubes that are around it. And it's really hard to explain, but intuitively it should make sense. There are 8 cubes surrounding this point, so 1/8 of the area of the domain around it should be within this cube. So 1/8 of A is in this corner, and this happens to be this chunk right here that Asano-kun tried to find the area of. Now notice that there are 8 other of these areas here for each of the 8 other points. 1/8 of each of their domains in which the point is closest to them are also inside this cube. So 1/8 times 8 corners equals A. So each of these corner pieces that we see here, each of the corner pieces actually add up to the same space inside this entire domain. The same space that the domain near the center point takes up. So A, which is taken up by each of these corner pieces, and A, which is taken up by the centerpiece, are added together, which is 2A, and that takes up the entire cube, right? And thus, the domain taken up by the center cube is A, and the total area in the cube is 2A, twice the domain. And thus, the domain taken up by the center point is half of the entire cube's area, or volume. And since I wanted it to be confusing totally purposefully, and I labeled the side length as lowercase a, that's the side length apparently, and the volume of the cube is a cubed. So that's the answer, a cubed over 2. Literally half of the area of the cube, which is much simpler than you think this complicated shape would have actually, taken up. It might have taken up like 1/3 or 1/6. No, it's actually just 1/2. And yeah, that explanation might be so complicated, but think of it this way. Think of it like Karma-kun this way. Every point is like a person. They're like your friends, and each friend has their own personal space. Everyone gets their own personal space, and an eighth of the personal space of these corners is in the cube. And since there are 8 friends around you with an eighth of their personal space within the cube, that means there's a complete personal space around your personal space in the cube, and your personal space takes up 1/2 the cube. Yeah, explanation metaphor wasn't really good, but I hope you found that problem interesting, and if you didn't understand it, hopefully you can comprehend my scribbles or rewatch the video. I hope you have a good one. Take out 1 cosine to the third theta, we get cosine third theta plus 3 cosine theta, cosine cube theta minus 3 cosine theta. Then we factor out cosine theta from this thing, and we get cosine cube theta minus